In this lecture, we're going to talk about three most commonly used numerical procedures in financial engineering, namely the tree method, or some people call it the lattice method. So we're going to talk about binomial trees and trinomial trees. We're also going to talk about Monte Carlo simulation and numerical solutions to partial differential equation. Now, when we work with the numerical procedures, it's important for us to be conscious about what probability measures that we're working under. Typically, if we want to price a derivative asset, it's probably the easiest if we work under a risk-neutral probability measure, such that if we are working under risk-neutral probability measure to arrive price, we just need to take a expectation under that measure and discount it to the current time. But there may be other situations that we probably don't want to just work under the risk-neutral measure. So no matter what probability measure we work under, it's important that we be conscious about that, and also be aware of, what asset we have selected as the numerator asset, so that because that determines what probability measure we're working under. So you will want to work under the risk-neutral probability measure. Particularly you want to work under the traditional risk-neutral probability measure. We want to select the money market account of the domestic currency as the numerator asset. Earlier, we have talked about certain adjustments that we may be needed to calculate the price of derivative asset. And if we were to work under numerical procedures, a lot of the times that we may not need to do those adjustments explicitly, because the way we handle our calculation inside the numerical procedure implicitly allows us to calculate the right price. But there may be certain situations that we still need to do an explicit adjustments. So I'm gonna show an example to illustrate in which situation you would need to do adjustments and in which situation you would not need to do adjustments inside of a numerical procedure. Now, as I mentioned earlier, that a natural choice of numerator is the money market account on numerical with domestic currency. And let's just review that and make sure we are clear on what we need to do if we select the money market account of the domestic currency as a numerator. So essentially, under that particular situation, the current price of the financial asset is really the expectation of the future realized value of the financial asset. Basically, here you will look at the payoff at the maturity time, and then you would discount that, and the discounting is based on the interest rate. Here, we have to do an integral because the interest rate at different time steps can be different. Now, if we were to do closed form solutions, and this may be an issue for us because we need to do an integration. But here, since we're doing numerical procedures, and we know the values at each time steps, we can just convert this as a sum, and so we discount it along each of the steps. So that would not be really an issue for us. So essentially, we to implement this condition here, we calculate and realized price, and we discount that realized price step to the step that is earlier. So we have the maturity big T, so we go by to big T minus 1. And then of all the values of the big T minus 1, we calculate an average, and then we discounted a step earlier to T minus 2. So if we're basically under a tree, that is how we're going to implement this particular condition here. So review lecture 3 and make sure you're comfortable with this, because this will be quite critical for numerical procedures. So when we do numerical procedures, we need to be consistent when we handled the different variables. You will handle price processes for different assets. They need to be consistent. And if we handled, price process and interest rate process, where the prices are interest rate related, then obviously those two type of processes needs to be consistent. Meaning that we can, let's say we have interest rate process and we have a process for zero coupon bonds or coupon bonds. We can't really specify them independently because, when we have a set of interest rate process, that process itself will determine the price of zero coupon bonds or coupon bonds. And the connection between the two is really Ito's lemma, right? So if you know a process for interest rate and if the asset is a function of interest rate, like a zero coupon bond, which is a function of the interest rate, then the price of the zero coupon bond is actually determined through Ito's lemma. So you can't really independently assume another process. So that's something that we need to be aware of when we implement numerical procedures. To look at the situation when we need to do an adjustment and when we don't need to do an adjustment, let's illustrate that with an example. Recall in one of the examples we had before, where we need to calculate the price of a contract V that provides a payoff in year 6, which equals the value of the stock index observed in year 5. So in this case, we need to do a timing adjustment. Now, if you do a numerical calculation on this, you actually don't need to do a timing adjustment specifically to calculate this, because the procedure itself will handle that. Now, what do? Let's say you are interested in the value of V at some, beginning of time 0 or current time. And if you have simulated your stock index at year 5, so at year 5, you have a number of unrealized stock index values. Here I presented 3, but you can, in principle, you should have a lot of those ones. Say you have 100,000 of them, right? And you also have the realized interest rate term structure at year 5. So here I is the realized index value of scenario 1, which is this particular point here for the maturity time T equal to 5. And also on this point, you also have a realized term structure interest rate. Now, once you have that for scenario 1, you know exactly what the payoff is gonna be at year 6. And you know exactly how to discount that value back to year 5 because you know the realized interest rate. Okay, so and then you have those value, and because you know the interest rate along the path, you can actually discount that value here. Well, you have this, you know the actual value here, you discount it to this point, you can discount it along every single point here due to the realized interest rate, and then all the way to get one particular value of V. You can do exactly that for scenario 2, for scenario 3. Each of them, you get a simulated value for that particular path for the value of V. And then you just average them, you know, take an expectation, take an average, you get the initial value, V naught. Now, if you were to approach your calculation like this, you don't need to do a timing adjustment because you know the detail of what the realized interest rate will be at every single scenario at year 5. And the reason you have to do adjustment earlier was because you don't have this granularity, you don't have the information under each scenario. All you have to work with is this condition where you needed a particular expectation. And you don't have this particular expectation. What you have is this thing here. And you have to have this thing multiplied by that. And this thing is the forward price. And this E, this forward price, basic expected value there. This forward price is the price that you actually observe here. It's the forward price observed at this initial time here for the index that is going to, for index value at this point here. So you only have one number, and that is that forward price, index price is not what you need. You need to adjust it. But here, you not just have this expected value of the realized index value here, you have the actual scenario here. And you not only have the actual scenario of the realized index price, you have the realized interest return structure per scenario as well. So given all those additional information, you then don't have to go through the convexity adjustment. You can just calculate them directly to get the price of V. However, if you say you're not calculating V, you are calculating an option C on V. So the option has a maturity time T here. So for each of the V value here, you have to calculate the option payoff, which is, let's say, is a call, so the V minus a K. So depending on which scenario, so you call this scenario 1, so V scenario 1 minus K. This will be V scenario at scenario 2 minus K. This will be the V value at scenario 3 minus K. Now, you can, if you have, you know, for each point here, if you've gone through a simulation to have the year 5 realized value of index and realized interest return structure, you know, you have a whole bunch of scenario here at year 5 plus T actually, then you can obviously do a, you know, simulation. You will have the simulated results. You can do a numerical procedure to calculate the V value here. And then obviously you're able to calculate the realized payoff for C for each of the scenario here, and then, you know, calculate an average here. So in this case, you don't have to go through a timing adjustment. But what you need to do here is for each of the paths you simulated, there is a multiple paths that you have to generate here. So you're basically wrapping a Monte Carlo simulation along a Monte Carlo simulation. So if you have like 10,000 paths you need to generate here, and for each of them, let's say you determine I need 10,000 paths to get your correct v-value for each of the scenario here, you have 10,000 times 10,000 simulation you really have to generate. So there's a lot of scenarios you have to generate, which makes it very, not very feasible. On the other hand, if you don't go through this, you only simulate the realized index value here and realize interest return structure at this maturity time of the option C. You then from this you can calculate the realized forward price. It's the forward price between this time and this time. Okay, so the forward price of the index, and then you do a timing adjustment, then you don't have to go through a simulation. Then you can calculate a whole bunch of v-values, a v-value for scenario 1, v-value for scenario 2, v-value for scenario 3, for each of the realized index value and realized interest return structure for each of the scenarios. Then for each of them, you can calculate the forward price, and you therefore go through an adjustment. You'll calculate the v-value for each of the scenario. And once you calculate the v-value for each of the scenario, you can calculate the payoff of the option C at each of the scenario, and then you discount that payoffs and take an average. You get your price of C. So if you were in this case going through a timing adjustment, you don't have to wrap a simulation within a simulation. You just have one simple simulation here. And if you need 10,000 scenarios, you have 10,000 scenarios. So here, you will have 10,000 times 10,000 scenarios. Okay, so that basically illustrates, what you need to, what are the situations you need to do an adjustment. What are the situations you don't need to do an adjustment here? Okay.